Hey guys, till now we studied about short transmission line and medium transmission line. We model the short transmission line by using a series impedance, and we model the medium transmission line by using a T circuit or a pi circuit. Generally we will be using the pi circuit. Why? Because this will not add an extra node. So what is the importance of this? You will appreciate this property while you are doing load flow analysis. If you observe the kind of analysis that we did for short and medium, we can infer two things. The first one is we have neglected some parameters. While coming to short transmission line, we neglected the shunt parameters completely. While coming to the medium transmission line, we neglected the shunt conductance. So, the first approximation we did is neglecting parameters. And what is the second approximation? We did a lumped circuit analysis. Lumped circuit analysis. So you may ask, what is the lumped circuit analysis? Let me explain this. Let me consider a transmission line of length L. Now I am dividing this into some units. If you observe each unit will have its own resistance, inductance, conductance and capacitance. But if we combine these all units into a single unit, and if we analyze the transmission line by doing this, then it is called as lumped circuit analysis. Now coming back, these are the two approximations we made. So why did we make these approximations? Why? Because line length is less. If line length is less, some of the parameters are not much significant. So we neglected and this worked. But while coming to the long transmission line, the line length will increase. So if line length increases, the parameters will become significant and each parameter will make some sense. We cannot neglect them. So as the line length increases, the importance of parameters increases. That is why we cannot neglect any parameter. So the analysis what we did for these two cases is not valid in the case of long transmission line. In other words, I can tell that we should do an exact analysis for long transmission line. So what is the meaning of exact? Here exact indicates the first point is we should consider all the parameters. And second point is, in generally transmission line will be distributed in nature, right? So we should do distributed analysis. So these 2 points we should keep in mind. With this motivation, we will move ahead and derive the equations for long transmission lines. Here is the representation we made. This is the receiving end, this is sending end, and the transmission line is of length L. At a distance x from the receiving end, I am considering a small segment of width delta x. The voltage at the starting of the segment is V plus del V and at the ending of the segment is V. Similarly, the current at the starting of the segment is I plus del I and the ending of the segment is I. Now let me define my parameters. If we see the series parameters, I am defining them per unit length. So my Z will be, let me represent this by using lowercase letter. My Z will be R plus J omega L ohm per kilometer. See, in transmission line, generally per unit means per kilometer because they will be in the range of kilometers. Next, let me define my shunt admittance. This will be G plus J omega C. My conductance and capacitance mho per kilometer. So these are the parameters per unit length. Now, if I need the impedance for the distance delta x, this will be Z into delta x, right? And if I need admittance for the distance delta x, this will be Y delta x. So is this clear? And this is the final simplified circuit that we designed for this delta x length. If you apply KVL here, what will be the equation? V plus del V minus V is equal to Z delta x into I, right? So from this I can write del V is equal to Zi delta x. Is this okay? Next, I will apply KCL here. So what I will get? I plus delta I minus I will be equal to Y delta x into V plus delta V. If I expand this equation, the answer will be YV delta x plus Y delta x delta V. If you observe this quantity, delta x is really a small unit and delta V is also small. If we multiply these two, then this quantity will become negligible. So generally we will neglect this. So after neglecting, what will be my equation? Y V delta x. From first equation, what you will be getting is del V by del x will be equal to Z into I. If this delta x tends to 0, then I can write this equation as dV by dx is equal to Z into I. I need to tell a point here. This V and I are dependent on distance. I mean, these are V of x and I of x. These are not constant values, okay? So, as delta x tends to 0, this dV by dx is equal to Z into I. Similarly, here del I by del x will be equal to Y into V. If delta x tends to 0, this dI by dx will be y into v. Is this okay? Next, I am double differentiating this equation. So, d square v by dx will be equal to z into di by dx. Now I am substituting the value of di by dx here. This will give rise to z y v, right? So d square v by dx square, this is square, is equal to z y v. From here you can write d square v of x by dx square minus yz into v of x is equal to 0. And you can easily solve this differential equation. The roots will be located at plus or minus root over yz. These are the roots, and the solution will be v of x will be equal to a1 e power root over yz x plus a2 e power minus root over yz into x. This is the solution for v of x. Next, I also need to find a solution for I of x, right? So, if you see this equation, dv by dx is equal to z into y. From here, I can derive I of x. dv by dx is equal to z into y. Now, I will differentiate this equation. What will I get? dv by dx will be root over yz a1 e power x root yz plus minus root over yz a2 e power minus x root yz. If I substitute zi in the place of dv by dx, zi will be equal to root over yz a1 e power x root yz plus minus root over yz a2 e power minus x root yz. Now I will divide this whole equation by z. So what will I get? Root over yz by z. This is equal to root over yz y by z. This is equal to 1 by root over z by y, right? So what I can write is this I is equal to a1 by root over z by y e power x root yz minus a2 by root over z by y e power minus x root yz. So this is the equation for voltage. And this is the equation for current. And this will be I of x. Let me put this in one page. In these two equations, apart from this constants, you are seeing another two terms, that is root over z into y and root over z by y. Let me define these two terms. The first one is root over z into y. We will call this as propagation constant. Propagation constant. And the another term is root over z by y. We will call this as characteristic impedance. This is nothing but impedance offered by a transmission line to the traveling waves. So the units of Z will be ohm. The units of Y will be mho. So if we see here, this will become ohm square and the final unit will become ohm. That's why we are mentioning this as an impedance. Next thing, if we multiply the numerator and denominator by length L, this will become the total impedance by total admittance. So while calculating the characteristic impedance, we can either take per unit impedance and admittance values or total impedance and admittance values. But while calculating propagation constant, we should take per unit impedance and admittance values. Keep this point in mind. The propagation constant is denoted by gamma and we denote the characteristic impedance by ZC. So I am using these two notations in these equations. This will become V of x is equal to A1 e power gamma x plus A2 e power minus gamma x. I of x will be equal to A1 by ZC e power gamma x minus A2 by ZC e power minus gamma x. And we can derive these values of A1 and A2 very easily by using initial conditions. We will derive that later, but there are some important observations to be made from these two equations. If you observe this first term, as x increases, let me denote this as 1 and this as 2. As x increases, the first term increases, and note that x is the distance from receiving end. Right? So as x increases, the first term increases, or I can tell that from receiving end to sending end, this first term increases. I can also tell this as from sending end to receiving end. Wait, let me put this as V1 and V2. From sending end to receiving end, the term V1 decreases. So while moving from sending end to receiving end, there is a decrease in the term V1. From this I can tell that this is a wave which is moving in forward direction, forward traveling wave. And similarly, if you see V2, if I increase the x, V2 decreases, or I can tell that while coming from receiving end to sending end, V2 decreases. So from receiving end to sending end, the term V2 decreases. From this I can infer the V2 is backward traveling wave. Backward traveling wave. So V1 travels from sending end to receiving end, while V2 is the wave that is traveling from receiving end to sending end, and the same thing is happening with the currents also. So from this observation, I am introducing you to the concept of wave traveling. That is, if this is first media, this is second media, there will be an incident wave which is V1 traveling from sending end to receiving end, and there will be a reflected wave which is V2 traveling from receiving end to sending end, and there will be some refracted wave. So this is the idea of wave traveling. Just to give you some sort of introduction, I explained this concept. We will discuss the concept of wave traveling in much more detail in next video. For now, we will just limit our lecture by deriving the ABCD parameters of long transmission line. That's it. We will see this wave traveling analysis in our next video. So here V of x is equal to a1 into e power gamma x plus a2 into e power minus gamma x, while I of x is equal to a1 by zc into e power gamma x minus a2 by zc e power minus gamma x. So now I need to find the values of a1 and a2 by applying the initial conditions. First, let me substitute x is equal to 0 here. That means receiving end. So what will be my equations? V of x will become VR and I of x will become IR. So the equations will be VR is equal to A1 plus A2 and IR is equal to A1 by ZC minus A2 by ZC. Let me find A2 from this. A2 will be equal to A1 minus IR ZC, right? I will substitute the same thing here. So VR is equal to A1 plus A2 is A1 minus IRZC. So 2A1 is equal to VR plus IRZC. From this, A1 is equal to VR plus IRZC by 2. Next, let me find A2. I am substituting the value of A1 in this equation. So A2 will be VR minus VR plus IRZC by 2. So this will become 2VR minus VR, that is VR minus IRZC by 2. Is this okay? This is the value of A2 and this is the value of A1. I am substituting in these equations. V of x is equal to VR plus IRZC by 2 into e power gamma x plus VR minus IRZC by 2 into e power minus gamma x. I of x is equal to VR plus IRZC by 2 into e power gamma x minus VR minus IRZC by 2 into e power minus gamma x. So these are the two equations that I can write. Now, to express these equations in terms of ABCD parameters, so what are the ABCD parameters? Vs Is is equal to ABCD into VR IR. We should express Vs and Is in terms of VR and IR. Then we will get ABCD parameters, right? So here, first let me take VR and IR common. What will I get? So V of x is equal to VR into e power gamma x plus e power minus gamma x by 2 plus IRZC into e power gamma x minus e power minus gamma x by 2. Next, I of x will be equal to VR by ZC into e power gamma x, there is minus sign here, minus e power minus gamma x by 2 plus IR into e power gamma x plus e power minus gamma x by 2. But if I need to represent these equations in terms of ABCD parameters, my left hand side should be Vs and Is, right? To obtain this, I need to substitute x is equal to L. If x is equal to L, then Vx and I of x will become Vs and Is, right? So I am substituting x is equal to L. This will become Vs is equal to Vr into this term is cos h gamma L. This is a hyperbolic function plus IR ZC sin h gamma L. Next, Is is equal to VR by ZC sin h gamma L plus IR into cos h gamma L. From this, Vs Is is equal to cos h gamma L ZC sin h gamma L sin h gamma L by ZC and cos h gamma L, this into VR IR. So these are our ABCD parameters by exact analysis. If you see here, A is equal to D and AD minus PC is equal to cos square h gamma L minus sin square h gamma L, which is equal to 1. The ABCD parameters are both symmetric and reciprocal. They should be symmetric and reciprocal. Why? Because this is an exact analysis. If you observe, we have not neglected any parameter. We considered each and every parameter and we did distributed analysis, right? So these are the parameters we are getting. But in terms of these hyperbolic functions, it is somewhat complicated to analyze. So in the next lecture, what we will do is, we will simplify this into T model and pi model by using Taylor series. After this, we will see the condition of lossless line and we will also see surge impedance loading, and some other things. After this, with the motivation that we got in between about the traveling waves, that is the incident wave and the reflected wave, with that motivation we will see wave traveling analysis. And this will end your topic of long transmission lines. See you in next lecture.